Hey everybody, welcome back. So today we're switching gears once again onto the topic of cosets. So very roughly speaking, cosets are a way of taking a group and somehow dividing it into pieces. And as we'll see, this can be useful sometimes for simplifying problems, like a kind of divide and conquer approach, or equating different group elements if for some reason you want to consider two different group elements equivalent to one another. So before I tell you the precise definition of what cosets are, I'm going to start off with a prototypical example. So for instance, let's consider the group Z of integers. I want to take that group and divide it into a few pieces. And there's definitely lots of different ways to do this. I could divide it into even numbers and odd numbers, or positive numbers and negative numbers. But a way of subdividing it that I think is helpful for illustrating the idea of cosets is to divide it into the following three pieces. First, I'll have the integers that are multiples of 3. So that'll contain 0, 3, 6, 9, and so on, as well as the negative multiples of 3. And then I'll have all the integers that are 1 plus a multiple of 3. So 1 plus one of the numbers in the list that I just wrote. And lastly, I'll have the numbers that are 2 plus a multiple of 3. Another way to say this is that I've taken the integers and I've divided them up into the ones that are congruent to 0 mod 3, congruent to 1 mod 3, or congruent to 2 mod 3. And let me highlight for you that every integer appears in one of these buckets. Maybe a good way to see that is to look down the line this way, and you see 0, 1, 2, 3, 4, 5, and so on. So you'll see all of the positive integers appearing there. And then looking maybe this way, you'll see -1, -2, -3, and so on. So all the negative numbers will appear as well. So okay, I claim this is a prototypical example of the idea of cosets. Let me now tell you the general definition, and we'll see how this is a special case of it. In general, let G be any group, and let H be any subset of G. In practice, in most of the examples we're looking at, H is going to be a subgroup, but it doesn't have to be for this definition to make sense. And finally, let little a be some element of... Sorry, there was a typo there at first. Little a should be any element in the whole group G. Then the left coset AH is defined as the set of all things that I can get by doing this particular element A and combining it under my group operation with any element whatsoever in the subset H. So this is going to form a subset of the group G. Before we look at an example, let me just point out that if the operation in our group G happens to be addition, we'll notate this a little bit differently. When we have AH, we'll write that as A plus H, because that's the operation. And this whole set, this whole coset, will denote by A plus capital H. So let's now look at an example to make this more concrete. And it'll be the same example, really, that we already saw. So let's let G be the group of integers where the operation is addition. And let's let H be all the multiples of 3, which is a subset of the integers. In fact, it's a subgroup. So now I can pick little a to be any integer I want. For instance, I could pick it to be 1, and then I'll get a coset, which I'm going to denote 1 plus h. And by definition, the elements of that coset are everything that I can get by doing the number 1 plus some element of h. So here I've written the elements of h in blue to try to highlight them for you. So the elements of 1 plus h will be 1 plus 0, 1 plus 3, 1 plus 6, 1 plus 9, and so on, as well as also the negative ones. So 1 plus -3, 1 plus -6, and so on. So if I do some of this arithmetic, you can write out what the elements of 1 plus h look like. They're 1, 4, 7, 10, and so on, as well as -2 and -5 and so on. So in other words, these are the numbers we met a couple of slides ago that are a multiple of 3 plus 1. So that's one example of a left coset, but I didn't have to pick the integer a to be 1. Remember, I can pick that to be any other integer. So keeping g and h the same, maybe let's try letting a be equal to 2. Then the elements of the coset 2 plus h are going to be 2 plus any element of h. So 2 plus 0, 2 plus 3, 2 plus 6, 2 plus 9, and so on, as well as the negative ones. And so in other words, what are these numbers? They're 2, 5, 8, 11, so on, as well as the negative ones. So these are the things that we met a couple of slides ago as 2 plus a multiple of 3. So that's a couple of different examples of left cosets in this particular group G with this particular subset H. And there's infinitely many more in this example, because I could do 3 plus H, or 4 plus H, or 5 plus H, and so on. But now let me take a look at a different example where the group is finite, because then in that case, I can honestly just list for you every single left coset so you see what they look like. So let's let G be the group Z6 under the operation of addition modulo 6. And let's let H be the subset that contains 0 and 3. So again, this is a subgroup of G. So now I can form a left coset A plus H for any A in the group Z6. And I'm going to run down all the 6 possibilities. A could be 0, 1, 2, 3, 4, or 5. If A is 0, that means that the coset 0 plus H looks like 0 plus something from H. So it's got 2 elements, 0 plus 0, which is 0, or 0 plus 3, which is 3. How about the coset 1 plus H? The elements of that are 1 plus an element of H, so 1 plus 0, or 1 plus 3. In other words, this coset consists of 1 and 4. And you maybe see the idea now. I'll show you what the rest of the cosets look like. The coset 2 plus H contains 2 plus 0 and 2 plus 3. So in other words, it contains 2 and 5. Here's kind of an interesting one. The coset 3 plus H contains 3 plus 0, so 3. And it contains 3 plus 3, which is 6. But remember, we're inside the group Z6 here, so 6 is the same thing as 0. The coset 4 plus H contains 4 plus 0 and 4 plus 3, which in this group is 1. And lastly, the coset 5 plus H contains 5 plus 0, which is 5, and 5 plus 3, which in this group is 2. I want to make a couple of observations about this example, but I'm out of room on this slide, so I'm going to flip to a new slide and rewrite these cosets for you. Okay, so what you see here in the upper left is just what we had on the previous slide, the list of all of the 6 cosets in this example. And the first observation I want to make is that all 6 of these cosets have the same size, namely, they each have 2 elements. And the second observation I want to make is that sometimes 2 of them are equal. For instance, notice here the coset 0 plus H and the coset 3 plus H contain the same elements. Similarly, 1 plus H and 4 plus H, those are the same set. And 2 plus H and 5 plus H, same set. So sometimes 2 cosets could be equal, but let me notice that when they're not equal, like 0 plus H and 1 plus H, those aren't equal. When they're not equal, they're totally disjoint from each other. 0 and 3, that has no elements in common with 1 and 4. So maybe a visual way to think about what we've done in this example is that we've taken all of the elements of Z6, so 0, 1, 2, 3, 4, 5, We've kind of chopped them up into these three buckets. In the first bucket, there's 0 and 3. Those are the elements of the coset 0 plus h, which happens to be the same as the coset 3 plus h. And then in the second bucket, there's the elements 1 and 4, which are the elements of the coset 1 plus h, and that's the same as the coset 4 plus h. And then lastly, there's the bucket that contains the elements 2 and 5, which are the elements of the coset 2 plus h, or in other words, 5 plus h. And so roughly speaking, what these two observations are saying is that this coset procedure takes the whole group Z6, it breaks it up into equal-sized pieces, and those pieces are disjoint from one another. So that's all in the context of this one specific example, but next time we'll state a theorem that collects these observations and proves that they work in general. So I'll see you then.